Hi, everybody. My name is Jared Longfox, one of the co-hosts of this AIAA Education and Outreach Space Resources webinar series. Thank you for coming today. Today we have Mr. Jason Schuler from NASA Kennedy Space Center SwampWorks here to present on an excavator concept that the folks at SwampWorks have been working on for quite some time. Jason's been with NASA for about 17 years, and throughout the duration of that, he's done robotics and ISRU work the whole time. But I'll let him tell you more about that. So, Jason, take it away. If you need anything, I will be here. But to save bandwidth, I'll turn off my audio and video for now.
All right, thanks, Jared. So I'm going to go ahead and get my screen on here. And I apologize, about halfway through, I'll have to unshare, turn on an audio so you can watch a narrated video, and then I'll reshare it. So,
And
uh,
sorry, I'm going to interrupt again. Folks, if you have questions or comments or anything, go ahead and punch them in the Q&A and we'll get to them once Jason's done presenting. So, all right, sorry about that. Go ahead, Jason.
all good. Yeah, perfect. And can I get a confirmation you can see my screen?
I can see your screen. Looks great.
Great, thank you. Okay, so I'm here to talk about a project that we're calling IPEX, the ISRU Pilot Excavator. This is a robotic excavator being developed under NASA's Space Technology Mission Directorate, the Game Changing Development Program, or GCD. So this is meant to kind of be an overview of what we're doing and why, and kind of give you a taste of the technical details. In the presentation, you'll see links to websites and other papers that dive into much more technical detail. And I'm happy to answer questions at the end, or if you want to get in touch with me after the fact to help answer any more questions y'all have. Okay, and there it goes. Okay, so I wanted to acknowledge the team. The picture is just a small portion of the team, but we have a fantastic and talented and dedicated team led out of Kennedy Space Center, supported at JPL. We have support teams at Johnson Space Center as well. We have folks on the team from Caterpillar, and it just wanted to thank everybody for all their hard work on this project. As you'll see as we go through, we're about halfway through development of this robotic excavator with this current project, but it's been an idea in the works for well over a decade. So it's been a long road, but we're getting close to something that's ready to go to the moon. So what are we doing? The idea here is a capability to do excavation on the surface of the moon and eventually Mars um, for multiple reasons. The first one is propellant production. We currently are using a methodology where all of our missions are supplied from Earth. Every bit of fuel that we need for our return trip home, we have to bring with us. We have to launch at takeoff from Earth, and it travels with us the entire time. The analogy I like to use is if your family's taking a road trip across country, you know, imagine having to tow a trailer behind you with all your gasoline, right? It's a pretty inefficient way to travel, but that's the best we have right now. But as NASA's trying to expand our missions and have a more sustainable profile going forward, especially as we approach Mars, the use of resources that we can get from our destination will really enable that. And one of the biggest bangs for a buck will be being able to refuel our vehicles, our rockets from our destination. So in the case of the moon, there's a couple options, right? You can look at the water ice and you can look at oxygen from regolith. IPEX is looking at the water, or sorry, the oxygen from regolith case, right? So, data we have from Apollo and orbital assets point to about 40% oxygen in the regolith, no matter where you are on the surface of the moon. So, this is an easy to reach resource that's abundant and it's impactful. It will equate to about 80% of the propellant that we need to refuel a rocket. So the idea would be, land on the moon, oxygen tanks are empty, your excavator goes out, collects the regolith, brings it to an ISRU plant that then heats it up, um, breaks the chemical bonds of the oxygen, recaptures the oxygen, and then uses it to refuel your rocket, and then you can take back off the surface of the moon. So it's a incredibly um, impactful capability. But to do that, you have to start with excavation, right? You have to actually mine up the regolith and deliver it to the ISRU plant that's going to do the chemical extraction. So there's some challenges in even just doing that excavation, and so that's what this project is looking to address. So here's kind of an overview I call like the envisioned future, right? You have this robotic excavator that's excavating significant amounts of regolith. You have some, different activities happening in the background, doing construction activities with the regolith as well, right? That's not, the construction activities aren't being addressed by this project, but it's kind of the next step, right? So we take this project, takes the first step to show that we can do excavation at scale, followed by excavation to do construction activities. Will be kind of the next big leap for this. Um, our project proposes to build a TRL-6 robotic excavator that's capable of moving 10,000 kilograms of regolith over 11 days. So the numbers there are significant. The 10,000 kilograms of regolith relates to the amount that you need to supply to an ISRU plant to extract 1,000 kilograms or 1 ton of oxygen using a carbothermal process. And that 1 ton of oxygen then could be used to refuel an ascent stage to take back off the moon. The 11 days relates to the amount of time that we would have on a lunar mission where we do not survive the lunar night. So this being a tech demonstration mission, we aren't manifested yet, but we hope to be able to demonstrate this technology on the surface of the moon. That's what we're designing towards. We, to keep costs down, tried to demonstrate this capability within 1 lunar day. And so about 14 days on average there, backing off with some margin, we settled at 11 days for this mission. There's some enabling technologies in this. So we'll talk about the low gravity excavation capability, right? Just doing excavation on the surface of the moon is challenging and requires a very different technique than what we use on Earth. And we'll talk about that in a minute. The robust lunar surface system reliability. This is operating in a really harsh environment. The regolith is abrasive and very fine, can be electrostatically charged. So operating in that environment, harsh lighting, radiation effects, we need to build a very robust platform from the ground up in this design. Dust tolerant battery charging and thermal control. This robot will be operating with this lunar regolith getting all over it, right? It's an excavator that's by definition going to get dirty. It's relatively low to the ground, and so we expect dust to be a big challenge for this robot. And so we'll talk a little bit about the strategies that we have to mitigate some of those challenges. This is also an autonomous vehicle, a supervised autonomous operation. We are far enough away, from the moon that and through the network latencies that you're not really going to be able to joystick this robot from Earth, right? We expect to have high-level commands that we send to the robot that the robot then um, executes on its own with our monitoring. Here at the ground stations, looking for any anomalies or waiting for the robot to phone home and said it got into a halt condition and wants advice on the next step. And then finally, one of the big differences here is the high cycle mobility. I like to talk about, the differences between like a Mars rover that we call a robotic scientist that has so many different instruments and can do so much fantastic science, has a lot of different jobs and a lot of complexity. This is the robotic construction worker, right? This has one job, excavate regolith, move it from point A to point B, and it does that job over and over and over again. And the rate at which it does it is much higher than what we've done before with other planetary robots. So again, simplicity and robustness are really important to enable that capability. So here's one of the fundamental challenges of doing excavation on the moon or Mars. You have to balance or actually have a higher drawbar pull or traction, basically, than you do the force of excavation, right? And so those are the equations that drive it. But it's that's actually pretty hard to do, right? Because when you're launching your excavator from Earth, you're putting it on a rocket. Right now, every kilogram we send to the moon costs about $1 million, and it's going to be significantly more than that when we send it to Mars. So we are very conscious about the weight and the mass of everything that we launch. So kind of by definition of budgets, it's going to be a low mass vehicle. Then you land it on the moon, which has 1/6 Earth's gravity. It doesn't weigh as much as it did on Earth. And so now you have to do excavation with a vehicle that has very, very low weight and low traction. And terrestrially, the way we do excavation is by having heavy vehicles. The more steel we put on our excavators, the more traction and downforce they have. And when they go to put their bucket down in the ground, the vehicle stays still and the buckets fill up with the dirt. And so we had to come up with a solution of how can you do excavation in this environment with such a low weight vehicle. And so this is the approach. This is the principal operation behind IPEX. We have digging tools that are called bucket drums that are on either end of the robot. And we'll talk a little bit about those more in a second. But as those digging tools are engaging the ground, digging the dirt, they do it at the same time, but in opposing directions. And so the forces that they generate from excavation, or the force that the excavation reacts, balances from either side of the robot. And so you no longer have to have that tractive force be the resistance to the excavation force. You can balance with the excavators themselves, and then just use your mobility system, the wheels in the middle, to efficiently control your movement of the excavator as it's driving. And so we'll show you some examples of that. This is the precursor to IPEX. This is what we called Razor, the Regolith Advanced Surface Systems Operations Robot. Razor is a Tier L4 robotic excavator built at SwampWorks, and the videos you're about to see are testing in our regolith testbed with a BP1 regolith simulant. The top left shows the normal mode of operation, right? And so this is the bucket drums down on the ground, um, and the mobility system driving forward at a constant rate. The drums rotate and you're skimming the surface, collecting a little bit of regolith in each of those scoops as it goes around. The regolith spirals into the center of that hollow drum. There's a like a baffle system inside that traps the regolith, and so it can be hauled in that same bucket drum as to your destination. Once you get there, you can reverse the rotation of the drum, and the regolith goes out of the scoops that it came in. All right, so it's kind of a two-in-one excavator hauler tool. We actively control the digging depth as we're driving, right? So we're kind of skimming the surface. So if you were to look closely, you probably can't see it over the internet, but the arms are moving up and down and actively controlling the digging depth of those cutting teeth as they rotate around. This enables us to ensure that the regolith goes in and doesn't jam at the cutting edge. It also helps us avoid things like rocks if we were to encounter those as we're driving, rocks that are too big to be collected. Down on the bottom, you're seeing a couple, on bottom left is a, contingency mode where you can use the arms and bucket drums as, a mobility enabler. So we don't expect in our mission to encounter rocks that we want to climb like this, but it really just shows kind of the capability of the system that you have inherently, right? We didn't add any extra capabilities to get this. This is actuation and torque that we already need just by doing the excavation. But now that you have this capability, you can use it for things like climbing out of trenches if you were to dig trenches to do maybe some bearing of equipment, right? For regolith shielding from radiation, for example. Things were to get stuck, you get in a situation where you need to climb out, you can use those bucket drums to help with that. And then the bottom right shows us driving up a 35-degree slope with almost no wheel slip. And again, that's enabled by the excavation tools, right? We have the bucket drums tilted forward. which shifts our center of gravity forward and puts weight over the front wheels, and it allows us to climb these really steep slopes successfully. So this is our Tyrrell 5 IPEX design. So we started with the Razor, with this GCD project, we started with the Razor 2, which is Tyrrell 4. This project was to take it from 4 to 6. We are at Tyrrell 5 right now. This is kind of the overview of that design. We scaled down from the Razor Tyrrell 4 version. This was in an effort to be able to fit onto a CLPS lander, right? So the idea that we would do our tech demonstration mission on a CLPS mission. So we wanted to just be a portion of the available payload mass on that. So our target was 30 kilogram excavator to go on a CLPS lander. And so volumetrically, it's about 70% the size of the Razor 2 design. Even scaled down, this excavator can collect 30 kilograms of regolith in its drums every time it fills them up. And it doesn't take long, only takes, about less than a minute to fill those drums up, and then you can go deliver it to where you need to. Four-wheel skid steer mobility system in the center there. You see the 4 wheels. We have 4 aluminum bucket drums, 9 actuators total. There's 8 cameras on board. Each camera's module has an LED system in it so that we can illuminate the terrain. We expect to be a South Pole region mission, so there will definitely be challenges with lighting and shadows. So we have the ability to illuminate that with the camera pods. We also have electrodynamic dust shields as lens covers for each of those camera pods. So again, I mentioned earlier the challenges that we expect to see with dust collecting on the surfaces of the robot. One of the ones we're most concerned about are the camera surfaces, right? Because we use those cameras to do navigation as we're driving around. And so the electrodynamic dust shields can repel and remove dust that has built up onto these lens covers. But that technology in itself is in development and has some upcoming lunar demonstrations as well. So as a backup plan, we also have a deployment mechanism on those lens covers. So it's a one-time deployment. If we get to a point where the EDS covers are not clearing the dust enough and it's affecting our ability to drive, we can jettison those lens covers one by one on cameras that are affected and extend our mission a little bit longer to get a little bit more data. Eventually, we'd expect those lenses to be covered with dust again as well, but it would allow us to at least extend the mission. We also do wireless battery recharging. So we don't have solar panels on board because they would get covered up with regolith and lose their ability to charge pretty quickly. So we have a large capacity battery on board and a wireless recharge system that's being built by Astrobotic and Ybotic. This is a space-rated wireless recharging system. And we come back to the lander to dock and align the wireless charger antennas, which recharges our batteries, and then we go back and continue our excavation. Similarly, we have a resettable phase change material to do our thermal control. So you would typically have a radiator surface on a robot like this on the surface of the moon to reject all the heat that the avionics and actuators are generating as it's operating. But if we have that radiator exposed, it's going to get a lot of dust on it and again lose its ability to reject heat. So our radiator is under a protective cover that is actuated. When the cover is down, the heat that the robot is generating goes into melting this phase change material. And then at the point where the phase change material is completely melted and can't absorb any more heat energy, we stop operation, open up that lid, exposing the radiator to space, which then resolidifies the phase change material, close the lid, and then go resume operation. So you can think of it like a thermal battery, right? And then I mentioned earlier that this is a supervised autonomous operation. So this is some of the hardware that we have right now. This is our Tyrrell 5 version of IPEX. And just to give you an idea of scale, this is your lunar dishwasher. So about the volume of just a standard dishwasher, right? Each of those drums and the wheels that you see there are about 12 inches in diameter. And then we'll talk here in just a second about operations in this environment that you're seeing. So I'm going to jump out for a second with my share and turn the audio on, and we're going to watch this narrated video about a recent test that we did, where it's essentially like a mock mission. We ran through the entire mission that IPEX would perform here at a test bed at Kennedy Space Center in August. So just stand by.
In August 2024, a team at NASA Kennedy Space Center completed a TRL-5 demonstration of the robotic excavator known as IPEX. The demonstration represented a mock mission with IPEX operating in an autonomy test bed that mimicked the lunar surface, and remote operators in a control room with appropriate time delays and telemetry. This video shows a summary of the demonstration with occasional insets of an animation from 2022 showing the progression from concept toward reality. The demonstration begins with IPEX mapping the surface. This is done by ground operators sending waypoint by waypoint commands approximately 1 meter apart. During these drives, IPEX uses fiducials on the lander to calculate its position on the surface and downlinks images from its onboard cameras. Operators use those images to identify hazards and plan the next waypoint. The images and hazards are then used to build a map of the landing site. Operators select the best locations for the loading and unloading zones, as well as the path between them. One of the challenges of operating on the lunar surface is the lack of an atmosphere. Because of this, thermal control is done by radiation. However, as an excavator, IPEX is exposed to a lot of dust, which can collect on radiator surfaces, rendering them ineffective.
Sorry, folks, I paused it there. I wanted to just check the audio cut out for me. Is it still playing for folks online?
Yeah, it was, at least I could hear it.
Somebody can type in the chat, or Jared can jump on and let me know.
Can you hear me, Jason? Testing.
Anybody hearing
Oh,
me?
hold on, everybody. I think we lost Jason's audio. Let me go to the chat.
Okay, I'm gonna stop sharing for a second.
Can you hear me now,
Can
Jason?
folks still hear me online?
Testing. Testing.
Okay, I think I saw somebody seeing it. Okay, I'm gonna keep going. Thanks. Sorry, I saw it in the Q&A. I think you guys might not be able to type in the chat, so I was looking in the wrong spot. So thank you, Kieran, for responding. I'll go ahead and continue it.
To combat this, IPEX covers its radiator with an actuated lid. When the lid is closed, a phase change material absorbs the heat energy until it is saturated. and a thermal reset is needed. IPEX stops moving, allows the dust to settle, and opens the lid, exposing the radiator. The PCM resolidifies, the lid is closed, and IPEX resumes operations. The dust would also pose a challenge for solar panels. So IPEX instead uses a large onboard battery that is wirelessly recharged at the lander. The wireless charger, designed by Astrobotic and Webotic, is tolerant to dust and has a large alignment tolerance. IPEX uses its radiator cover and arms to align to the wireless charger. This approach gives IPEX multiple degrees of freedom to adjust its charger alignment, which reduces risks related to unknown terrain conditions. Once complete, IPEX lowers back to the ground and resumes operation. The majority of the mission time is spent completing reps, which is a cycle of loading regolith, driving 100 meters, unloading regolith, and driving 100 meters back to the loading zone. This is done in a supervised autonomy mode, where operators command IPEX to complete a rep or series of reps, and only intervene if an anomaly is detected. During the demonstration, the operators had limited telemetry and a 14-second round-trip time delay, simulating the operations on the moon. Simulation coordinators, or SimCs, monitored the operations real-time with overhead camera views like the ones seen in this video, live telemetry, and e-stop control. The SimCs captured the difference between what was actually happening versus what the data-limited operators thought was happening. On a few occasions, IPEX got hung up on unseen hazards. However, the operators were able to identify the problem with their limited data and use methods like driving on the bucket drums to recover. At the conclusion of the demonstration, IPEX completed 334 reps, which is equivalent to the project's goal of moving 10,000 kilograms of regolith. This was done over 205 hours, leaving nearly 60 hours of margin in the 11-day mission timeline. For more information, visit www.nasa.gov/ISRU-pilot-excavator.
Okay, so I just got to reshare my screen because that takes over my mic when I do that. So let me get back.
Can you hear me, Jason?
I can now, Jared. I think it was on my side. I wasn't getting audio out, so I can hear you now.
Yeah, no problem. We could hear you. You just weren't hearing me. So, great video. Continue.
Cool, thanks. Okay, so with that demonstration, we had a max drive speed. We actually started at around 30 centimeters per second, but during the demo, we started to try to push it a little bit further, see what we could get up to. So we got up to 40 centimeters per second. Again, tracking the lander, looking at the different fiducials as was driving around. We had about 35 battery recharges throughout the mission. Those are all automated, the docking procedure that you saw there. We did 10 reps per battery charge, got to down about 9 minutes per rep. 68 minutes was our default battery charge time, and our thermal reset was 121 minutes. Both of those were just simulated. We went into the position. You can't actually do a thermal reset in this Florida ambient environment, right? When it's designed to operate to do that on the moon. So we got into position and then just jumped the mission clock ahead 121 minutes and then continued with the demonstration. Similarly for the battery charge, we docked, did the alignment. It is a functional battery charger there, and we confirmed that we had current flow. But instead of sitting there waiting for the whole 68 minutes with operators operating around the clock, we wanted to try and shorten it up as much as we could. So we just jumped the mission clock ahead the 68 minutes, and we had external batteries that we could go swap out if those got low enough. The total reps was 334. The distance traveled that on that demonstration was a total of 58 kilometers, 58.1. So if that were to have been done on the moon, that would have set a new record for the distance traveled on another planet. So currently the Opportunity rover has the record at 45.2 on Mars. And so this is looking at our timeline for the mission as it stands coming out of the demonstration. So we have about 8 hours for deployment, 15 hours for mapping. The excavation reps take 182 hours, and that leaves us with 59 hours of margin in our mission timeline. I have some notes here. Our KPP, which is our key performance parameter, is half of the 10,000 kilograms, so 5,000 kilograms of regolith excavated. And the reason we chose that as kind of our like threshold, right? That is saying like if you can at least do 5 metric tons of excavation, you can still meet the needs for ISRU systems, because these ISRU studies have been going on for a while, have assumed more than 100 kilograms for an excavator that can do this capability. So us being around 35 for the excavator right now, we could send 2 of them. We could scale up and do a larger one. So even if we get to 5,000 kilograms of excavated regolith in this mission, we think we've met the threshold for success. But our goal is 10,000, and as it looks right now, it looks like we have plenty of time to be able to reach that goal. So I did want to mention a paper that we did for the Ascend conference recently. This is on our TRL5 subsystem. It goes into, or sorry, our 205 design, it goes into detail on all of the subsystems that we have in our current design. So subsystem by subsystem, what actuators are used, bearing specifications, a lot of detail, so that if folks are interested in getting some of that technical information, this is a really good resource for that. You can scan the QR code, or we can provide the link later. I wanted to, in the next slide, just kind of give you a feel for what kind of technical information is in that paper. Again, actuator design, we have like breakout drawings of the housings and the assembly stack up of each of the actuators. We talk about the testing that we've done with these actuators. So to get to TRL5, which is, I saw a question earlier, TRL is technology readiness level. It goes from 1 to 9, 1 being like a brand new idea concept. You can write a paper on it. 9 is something that is flown in space, is qualified to go fly again on, some sort of critical mission. So 4 is where this project started with picking up from Razor. We're taking it to 6. 6 is the level that you would need to be at to then go do a demonstration on the moon. The demonstration is just that. It's a demonstration. It's not tied to any larger mission where it's a critical component of that mission. This shows that you can actually perform the functions that your technology is required to do, and then after that demonstration, then you can rely on it on a larger mission where it's a critical element. For TRL5, we have to do testing in relevant environments. And so for us, that is vacuum, that's thermal, regolith dust intrusion. And so you're seeing some of those tests here. We have thermal vacuum chambers where we put regolith simulant in, look at the dust intrusion into the seals and into the bearings, and looking at how that affects the performance of the actuators. All of this is in the paper that I mentioned. Look at the power draw across we run through the full concept of operations with these actuators inside their thermal chambers, thermal vacuum chambers, and look at their performance over time. Again, breakouts of all the different actuator housings and components, talks about the test setup for some of these thermal vacuum chambers, which in themselves are a pretty unique capability. We do characterization on all the actuators. We use the current feedback from all the actuators to infer the torque, which then tells us how much regolith we have in the drums or how much load we're imparting into the ground during excavation. And we don't just use like a current value for that. We actually characterize the performance of the actuator through different variables: temperature, different voltages, different torques, and basically create a data set that we can use to more accurately estimate the output torque at any given current. We talk about the camera testing. This is a picture of the vibe testing that we did on that assembly. Also thermal vacuum chamber testing on the camera assembly itself, looking at distortion on the lenses, look at the regolith buildup on our radiator cover and how that regolith may fall off the radiator cover as you open and close it, trying to protect the radiator underneath. So, so all of that and more is in that paper. So please encourage people to take a look, and if there's questions, just reach out. It's a big goal for this project to try to get as much information as we can out into the community for folks that are interested in doing this type of work, so that we can kind of build upon the work that the IPEX team has done. So this video here shows a experiment that we're gearing up to run here, hopefully in the next few months. This is set up for a suborbital reduced gravity flight. So this will be an automated experiment running on its own. We'll get about 2 minutes of of lunar gravity levels. And we have a vacuum chamber here, a custom vacuum chamber housing 3 different bucket drum sections. The sections are just kind of like one slice of a bucket drum, and you can kind of see the baffle spiral that I talked about earlier that's inside. These sections are, have polycarbonate lids, and they're backlit, so you can see the flow of the regolith inside of them. And these are scaled down just so we could fit in the space that we had available. But what we're doing here is trying to validate a discrete element model of the flow of regolith inside of a bucket drum at vacuum and lunar gravity levels. So one of the risks that we're carrying on the project that we're hoping to close out here with this experiment is the risk of regolith jamming inside the bucket drum, right? If the gravity levels are lower and you're not pulling down on the regolith as hard as you are on Earth, you have this very fine grained material and maybe some vacuum effects that maybe could affect the charging of the particles. How will the regolith flow in that environment? Will it get jammed up in between the baffles inside the drum and not flow back out? So we've created a simulation of this setup, and we have 6 different bucket drum sections. Because we have 2 experiments we're flying at the same time. They have different spiral geometries. They have different regolith simulants inside, and then this data, once we get it back, will then go to informing that model that we have. So then we can use that model simulation to optimize the geometry that we go with for our final version of IPEX. Okay. I think one of the last slides I wanted to mention this Lunar Autonomy Challenge that was kicked off recently or announced recently. There's signups are ongoing. This is a collaboration between Caterpillar, Johns Hopkins Applied Physics Lab, Embodied AI, which runs simulation challenges. And the idea here is to have university teams develop autonomy software to drive IPEX in a simulated lunar environment. This is run in Unreal, and it will eventually go through the full excavation, the full ConOps of what we're doing on the IPEX mission itself. And to the level of it even will interact with the regolith, have forces that are generated back onto the robot itself, and see how that affects the autonomy software that these teams are developing. This is a brand new competition, so this first year is more about mapping the environment and grading teams on how well they map the environment just using the limited sensor set that we have on board IPEX. Caterpillar is really interested in this. They're one of the primary sponsors because they're an autonomy company, and most people don't recognize that, right? They see them just as a mining company, but a lot of their mining vehicles are being switched to autonomy modes, and so they want to increase their visibility with universities and fresh out students, so they can recruit some of the best and brightest. So they're making some of their simulation capabilities, which are typically proprietary and unavailable, open in this challenge to help train up some of the students. So it's an exciting challenge. And then just to wrap it up, some next steps for this fiscal year, which runs October to September for NASA. We just completed a series of reviews. They were done subsystem by subsystem, what we call preliminary design assessments, or PDAs. And then we wrap that all up into like a full system-wide preliminary design review. And so that's at the 45% level for this development. So we're basically saying for the TRL-6 version that we're saying will be flight ready, ready to go to the moon, we're essentially at 45% there on the design. And we've passed all those reviews. So we'll be flying our suborbital bucket drum experiment in the next few months. We'll be implementing design updates that we've learned in this TRL5 iteration, and then moving into TRL6 environmental tests, which will combine subsystems and increase fidelity, being closer and closer to that flight-like version. And then wrapping up this fiscal year at the end of September with our TRL6 critical design review, and that's equivalent to the 90% design level. And I think that is everything I have. I will plug that there is a website for IPEX. It's publicly available. We are posting all these pictures and videos, all these reports and presentations there. So I encourage you to go check it out. If there's something you're looking for, there's a good chance it may already be on that website. If not, please reach out to me and happy to answer any other questions. Thanks.
Awesome. Thank you, Jason. Great talk. Can you still hear me?
Yes, I can.
Okay,
Thanks.
awesome. Yeah, thank you very much for going through all of this. We have several things in the Q&A, so I'll just jump straight into that.
Sure.
Anonymous attendee asks, some folks watching may not know what TRL means if they don't work at NASA. I heard you address that, so thank you. Is another anonymous attendee, or possibly the same one, I have no clue, asks, is that video you showed published on a public site where we can view and share?
Yep. So if you go to this ISRU pilot excavator site, all those videos are there. Yep.
Awesome. Thank you. Then Andrea Rotoloni asks, what kind of mechanism do you use to simulate the moon gravity?
Okay, so we have done some gravity offload tests. We don't have a very advanced rig here at this lab, but we have a gravity offload rig that essentially is like a gantry system that can follow the robot, but it's not active. So we set up a pulley system and we put 5/6 of the robot's weight on the opposite side of the pulley, which offloads its kind of base weight. And we've proven the kind of fundamental capability there of balancing your excavation forces with the dual acting bucket drums digging in the opposing directions. And in this experiment, we've done this, if you put one set of drums down under that gravity offload condition, and you just try to dig with one set without the other set balancing the forces, you happen to get some regolith in the drum, but it's extremely uncontrolled, and you end up really just pushing the robot along the surface, right? And Then when you put the other set of drums down, the robot stops moving, and you can just very easily control your movement just with the wheelbase, because you're no longer fighting the forces of excavation. Great question.
Makes sense. Same person, Andrea asked, is it possible that the moon's gravity will interact with other processes, such as battery charge?
I don't see anything really on the battery charging process. Anything with regolith flow, we're certainly looking at. And so that's why we have that experiment I was talking about with the reduced gravity flight. But it's not just this system, right? So we are bringing this regolith back to a processing plant. Right now, it's for ISRU, so we can get the oxygen out. But in the future, it may be a construction process, right? And so it is really important to consider how regolith flows through all these different systems, because it's a fine material. It's different than a lot of the materials we have on Earth. And then in that reduced gravity environment, it definitely can behave in unexpected ways. So something we're looking at.
Absolutely. Excuse me. So Andrea asks, can you send me the slides and provide your contact information? Actually, I mean, yes, Jason can probably do that, but the slides will be publicly available shortly after this talk, within the next couple of days, at on AIAA Engage. It's AIAA's platform where the technical committees, which this is put on by the AIAA Space Resources Technical Committee, where we can post documents for either the technical committee members or the general public to access. And I'll be putting them on the public forum. In the chat, which, oh, that was just to hosts and panelists, so attendees can't see that. Let's go, everybody. Delete, copy. Sorry, folks. I'm trying to paste links to the YouTube channel where we post all of our recordings, as well as where we put the AIAA Engage slides. I'll work on doing that while Jason answers another question, because my copy paste isn't wanting to work from the chat. Anyhow, so Andrea, we can get you the slides that way, if that's cool with you. Carol asks, will the recording be made available? Yes, absolutely. I will get that link in the chat in just a second. Then Karis Cosmos asks, what is the assumed soil temperature envelope?
So we are, like I said, a South Pole region mission. I don't know what exactly we put in as our thermal regolith temperatures in our thermal model. We have a full transient thermal desktop model to simulate this, but I do know that the operational limits, like our allowable flight temperature range, is I think around -40 C to about 80 C, and that's held within those ranges by our phase change material and our radiator surfaces, and like the finishes on the robot itself would help reject the heat. So sorry, I don't have exactly the numbers you're looking for, but hopefully maybe that helps a little bit.
Awesome. Thanks, Jason. And to go back to the point, everybody now in the chat, you should have two links. One to the AIAA Space Resources Technical Committee's YouTube channel, where all these videos are, and this one will be in a couple days, and the public forum for AIAA Engage, where the slides will be. I will note we're having some technical issues on the AIAA end with actually uploading files, but I'll get them uploaded as soon as I can. So anyway, thank you for answering that thermal question, Jason. Karis also asked, what is the efficiency of power transmission for charging?
So right now we have a requirement that it's at least 60% is the goal. We're seeing maybe even closer to 70 will be a reality, but we think a minimum of 60.
Cool. Anonymous attendee asks, IPEX is a cool and technical name for this robot. I'm curious, what do you and your team call the robot informally, internally? That's a cool question.
Yeah, that's a good question. So for this first version that we did that mock mission you saw the video for, we've been calling that version AlphaBot because it's the first one, first time we've assembled this version of the robot. So we've been calling that one AlphaBot. I don't know if we're going to continue the trend and have like a beta bot and going from there. But some other internal names we've talked about. We have a camp in the team that really likes and wants to call the robot Darth Excavator. So there's even been some logos that have been generated. So we'll see what happens with that.
That's cute.
Yeah.
Hunter Williams asks, or
Hey,
well
Andrew.
says, Kurt made a teaser on LinkedIn about a month ago about IPEX. Can you say if you've been manifested for a flight to the moon?
We have not. We are um, working under a plan to take it to TRL6 to be flight ready. We're going to do all the qual checkouts and acceptance testing and everything, all the paperwork to make this ready to fly. We'll be done with that the first half of fiscal year 27. So if we can get a flight between now and then, that's when we would start integration into a lander. So that's our hope. Worst case scenario, if we don't, we will have that hardware ready to go, and we will keep it in bonded storage until we do get that flight.
Awesome. Fingers crossed.
Yeah.
Mike Lucas asks, in the suborbital flight experiment, there are two sets of two circular areas on the transparent window on the bucket slice in your video. What are these circular areas?
Oh, I think I know what you're talking about. Let me zoom back up. So you're probably talking about these little discs, I imagine. If that's what you're talking about, Mike, these are vents because we pull a vacuum. This is in a vacuum, a custom vacuum chamber, and so but then it's an enclosed volume, and so because we didn't want to have trapped air inside of here, we have these kind of like filter vents that help the air release. Hopefully that's what you're
Perfect.
referring to. Yeah.
Might go ahead and punch in the Q&A if that was it or not. But we'll move on for now. Andrew Rotoloni asks, what kind of mechanism erosion will the excavator have to its structure?
Um,
So
okay, so we're saying, yeah, how much erosion are we expecting on like
mhm,
mechanisms, maybe?
yep.
So that's part of the testing we're doing in the thermal vacuum chambers with the Regulus simulants, and we've gotten like high fidelity simulants to try to recreate that as much as we can. We don't expect that we will have any failures in the mechanisms for the life of this mission, so we can do the 10,000 kilograms. We have margin. It's not crazy margin. We think we'll probably um, you know 3-4 times the lifetime, and then you start to maybe see occasional failures of things like seals or rotating mechanisms. Um, so we should be fine for this mission, but this is really the tip of the iceberg, right? We want to do much more in terms of ISRU, much more in terms of construction. So there's going to need to be follow-on projects that look at you know even better sealing approaches if possible, and then eventually when we just can't engineer it all out, how do you do repair and maintenance robotically? Because you're probably not going to have astronauts there all the time to do it. So how do you swap components that have failed for replacements, just like we do on terrestrial mines. So that's definitely on the horizon.
Awesome. Awesome. Kieran Carroll asks, can you provide your email address? And I can punch that if you want me to, I can just punch that in the chat real quick.
Yeah, sure. Yep, you have it, Jared. So go for it.
All right, I did punch it in the chat for participants. Everyone should be able to see it. It's jason.m.schuler@nasa.gov. Perfect. Confirmed that is what Mike was referring to. He asked because it looked like some simulant was getting hung up on those areas, those vents.
Yeah, they're adhesive. So yeah, right around the edge, you get a little bit of stickiness. But the good news is they're extremely flat. They're literally paper, right? They're like a
Nice.
filter paper. So
Cool. Oh, Andrea, for access denied to AIAA Engage, you do have to have an account. It is free to make that account. But if you're an AIAA, so for AIAA, you can pay to be a member. You can have an account without paying dues, though. So if you have an account, please make one. If not, I will punch my email address in the chat right now. So you can contact me separately. Sorry about any inconvenience there. You have an account, but it doesn't permit you to download files. That's interesting. I will look into that. Thank you. Kagri Kilik, I am so sorry if I butcher your guys' names. How do you deal with the wheel slip for localization purposes? Do you have any force torque sensors for terramechanics, or is it just utilizing the visual odometry / IMU / wheel odometry?
Yeah, so for localization, it's what you said, it's the visual odometry, IMU, wheel odometry, but it's also and critically lander localization. So that is our absolute localization method. So right now it's looking at fiducials on the lander to judge the robot's location. As we move forward, we're going to try to reduce the number and the size of the fiducials. We're also going to look at, or we are looking at, recognition of the lander itself and features on the lander that you could use kind of as a nav aid. But that helps us eliminate some of the drift that you have from just using like VIO and wheel odometry. And then in terms of the force torque sensors, we don't have an explicit one for any terramechanics measurements or things like that. It's really just going back again to the current measurements, but we have really characterized those current measurements. So I think we have a good deal of fidelity there. And it is just mostly to reduce complexity in the robot, right? We've looked and talked about adding those sensors in, but really just trying to push hard on keeping this as simple as we can. So we think we can do what we want to do with just the current feedback.
Awesome. Well, we have 2 minutes to go. I'll wait a second, see if anything pops into the Q&A at the last second, but to prepare for closing, Jason, thank you. This is an awesome talk. Lots of really good questions. I hope everybody here enjoyed it. Please note, this is the last Space Resources webinar of 2024. So Jason, thank you for helping us close it out. We'll be back in January 2025, so stay tuned to your emails and social media for that announcement. But thank you all for making this a success. It's a lot of fun to do. I hope you all enjoy it. Please feel free to contact me or Joe Kenrick, the co-organizer, with any suggestions on how to make this better, topics for webinars, and so on. So with that said, Jason, do you have anything else to add before we go?
Thanks for the invite, Jared. I really appreciate doing this, and happy to answer more questions if folks need to email me and want to reach out. Otherwise, have a great holiday, everybody, and Happy New Year.
Awesome. Thank you all. And yeah, happy holidays, happy new year. See you in January. Bye, everyone.
All right, bye-bye.